nice when technology works. Right. So in our last section, we were looking at. The topic of the section is the fascinating physics of everyday life. Basically, what we are attempting to do in this section is to sort of go through some of the physics concepts, very basic physics concepts that sort of play out in our day-to-day activities. We saw that physics extends well into our everyday life, like I tried to explain in the last section, describing motion, forces, energy of ordinary experience. In actions such as walking, driving a car, or using a phone, physics is at work, and for everyday living, all the technologies you might take for granted exploit the rules of physics. For example, your phone. How is it possible for you to dial a combination of numbers on your keypad, and then you hit a dial button, and then you are able to talk to somebody thousands of miles away in a different continent? How is that all possible? How does your speech talking into a phone gets to the person that is in America? You're talking to a phone, the phone is not connected. You physically can't see the connection between your phone and anything outside the phone, but yet someone in America can clearly hear you. How does all that happen? The truth is that physics can explain all that, right? So that's basically what we are trying to do in these sections. Discussing some of those simple basic physics concepts and how they relate to what we do in our day-to-day activities. I try to give a quick introduction by saying that physics is a branch of physical science that deals with the study of physical phenomena. And what I meant by that is that when you look around you, there are so many things that happen around you. The sunrise and the sunset, difference in seasons, throughout the year, rise in the sea level and all of those things. You can basically explain every of that. Whatever you see happen around you in nature, there's always a physics principle or concept that explains it. The rainbow, the colors of the rainbow. How does the color of the rainbow form? You can explain that by basic physics, right? I know there are other explanations to the rainbow anyways, but when it comes to science is evidence and fact-based. And when you see certain things occur in nature, you can basically explain them using physics principles. Some of these things that I've mentioned, like some of these occurrences that I've mentioned, I might not talk about them as we go along, but if anyone pricks your attention, for example, when I said you can explain rainbow using physics principles, and you wish to know how you can actually explain that by physics, you can ask a question on that later, and I will explain. Okay? So let's just go on for now. So I said there are different branches of physics. I tried to explain that there is a branch called classical physics, and you also have what we call modern physics. They are not types of physics, please. They are just branch or areas of physics. There's no such things as type of physics, right? So they are just branches or areas of physics. Classical physics, from the word classical, means old. So those are the foremost areas of physics that physicists try to concentrate on, things that bordered around physical objects, their motion and things like that. And I try to name a few physicists, renowned physicists as they were. I mentioned an example, which is Isaac Newton. Which is the person I'm currently pointing to. Isaac Newton did a very interesting work in physics. So he's called Sir Isaac Newton. I have a very terrible handwriting. I should have been a doctor. Isaac Newton, did a lot of work in motion, equations of motion, laws of motion, and he also tried to explain some of the, motion of the planets, what they call planetary motion. So some of the work of Isaac Newton is what made it possible for us to be able to travel to the moon, right? And understand how the different planets, orbit around the sun. Okay, people like Isaac Newton did a lot of work on planetary motion, and also another guy called Kepler. So Kepler was also another man that did a lot of work on planetary motion, and we have some laws called Kepler laws of planetary motion, which is derived from the basic equations of motion by Isaac Newton. Another interesting man next to him there is Galileo Galilei. Galileo Galilei also did a lot of interesting work as well in physics. Basically, the idea of gravity and gravitation. Galileo Galilei did a lot of work on that. Galileo Galilei is originally from Italy, a place called Pisa in Italy. Those two guys did a lot of work, in what we call classical physics, which sometimes we call mechanics, as it were. Mechanics, yeah. So mechanics, or mechanics is just an area of physics that deals with motion, basically. So under mechanics, you have things like dynamics, and you have things like statics. So under mechanics, you can have dynamics, and then you can have statics. So dynamics deals with motion and force, right? Statics, from the word being static, deals with properties of body at rest. So we talk about statics. So when we are talking about friction, okay, before a body starts to move, or you're talking about the weight acting on the body as it stays at rest, all that is statics. Below Isaac Newton and Galileo Galilei is another man called Max Planck. We have Albert Einstein, and then we have Stephen Hawking. These three guys, you can basically say, are modern physicists. So they did it, their work in physics dates after, from the early 19th century. So from the 1900s upwards, they did a lot of work in physics. So they are called a modern physicist. And they are also called theoretical physicists. As it were, you can call these guys practical physicists because, they deal with tangible objects and things like that. Why these guys are theoretical physicists or modern physicists? Because most of the things they did were just basically things you can't actually see with your eyes, so you can just imagine them. So people like Max Planck, who did a lot of work around the behavior of particles, we have what we call the Max equations, E equals to hf, that simply talks about the energy, of a particle that moves with a certain frequency. We have people like Albert Einstein that equally did a lot of work on particle and wave behavior, right? How light travels through a medium, and he tries to describe light as both a particle and a wave. And he talks a whole lot about photons, behavior of light particles when they hit a body. When a material is heated by light, it emits certain particles called photons. All right. Sorry, when photons, hit a material, photon is simply a light particle. So when it hits a material such as a metal, certain other particles are released from that metal called electrons. So that behavior is called photoelectricity. And those are some of the things that people like Albert Einstein did. Basically, Max Planck, Albert Einstein, and Stephen Hawking, did a lot of work, around, particle behavior and things like that. Stephen Hawking, which is this guy. So this guy is Max Planck. This guy is Albert Einstein. And this guy is Stephen Hawking. Until his death, Stephen Hawking was stationed in Cambridge, okay? He did a lot of work in Cambridge and Oxford, and he was a theoretical physicist. What he tried to do was to unify the theory of these two guys and these two guys. To get one single theory, he tried to call unified theory, combining mechanics and relativity to get a single theory. Very interesting guys, actually. Let's not waste too much time. I gave some quotes from them the last time, very interesting quotes as well. We went on to talk about physical quantities, where I said physical occurrences can be measured using physical quantities. And I said physical quantities simply describe or they measure a physical phenomenon. And then we went on to talk about the two types, which are the fundamental, or also called basic, and the derived quantities. And I said these are some of the fundamental quantities like time, mass, temperature, electric charge, length, mole, which is the amount of a substance, photon of light, which I mentioned about the last time. And these are all derived quantities because they are formed by combining one or two of these other fundamental quantities. We went on to talk about vector and scalars. And I said vectors are simply quantities that have size or magnitude, while and also they have direction. And I said scalars are the ones that have only size or only magnitude. We saw some examples of those the last time as well. We then went on to talk about motion, and I simply said a body is said to be in motion when its position in space is constantly changing with time. So whenever a body position in space is changing with time, the body is said to be in motion. And these are some types of motion. So translational, for example, a car moving, or a cyclist, or somebody walking on the road is undergoing a translational motion. Circular motion, which is motion around a circular path. Rotational motion about a fixed point. Brownian motion is just a very random motion. It's also called random motion, or a motion whose pattern is not well defined. So it's sort of zigzag, okay? A very common example of Brownian motion in nature is how molecules actually move within a medium. For example, the particles in your blood, or the nutrients in your blood, you know, all the blood components, the hemoglobins and all of those things, they all move in a motion called Brownian motion in your blood streams. Another example is also the motion of what we call polygrains. Polygrains are certain things that the flower produces, right? So Brownian motion, when you have a droplet of water on a flower, and there are polygrains drop on that flower, their motion can be described by Brownian motion. And that motion was first described by a man called Gordon Brown, right? It's actually very important, actually, in real life, because this motion is responsible for a type of fertilization in flower called self-fertilization. So before a flower can be fertilized, there has to be a motion, there has to be a movement of the pollen grains from the anthers of the flower to the stigma of the flower. And one example of such process is called self-fertilization, where that movement occurs within the same flower, all right? So that type of motion can cause self-fertilization in flower, which is the Brownian motion. Then you have a projectile motion. This is responsible. This is the type of motion that some astronauts can use to launch a rocket into space. Also, when you hit a baseball and it goes in a curve pattern, that type of motion is also projectile motion. Then you have rectilinear motion, which is motion along a straight line. For example, the motion of a light photon, okay, or a wave of light undergoes rectilinear motion. I tried to explain the difference between circular motion and rotational motion the last time. Some of us didn't really get it, but you can just, from this illustration, see the difference. So this is basically circular motion, which shows the motion of the planet around the sun. Okay, now if you take the sun to be the center point, and you have all these tiny planets revolving in their individual orbits around the sun, this is circular motion, okay, because they are actually not touching that center point. But the other type here, this is much different, because this is essentially rotational motion. So you have the Earth rotating about a fixed point. So the rotation of the Earth is, this will be a rotational motion, while the first will be a circular motion of a different planet around the sun. Okay. We went on to talk about equations of motion. I didn't have time to really go through this because yes. Right, so we went on to talk about the equations of motion, where I simply said that, okay, there are three basic equations of motion, right? We have the first equation, we have the second equation, and we have a third equation. These are equations that describe the motion of a body, describe the linear motion of a body, right? And if you see in each of these equations, you have different quantities. You have velocity, you have acceleration, you have time. Here you have displacement or distance, you have velocity, you have acceleration, and you have time. In the last equation, you have velocity, you have acceleration, and then you have displacement. Later on, we are going to see a question where we can apply this equation. Next, we talked about the laws of motion. And I said there are three basic laws of motion. There's the first law that says that a body will maintain its state of rest unless acted upon by an external force. okay, a body will continue to stay at a state of rest, except you apply an external force to cause that body to change its state, which is to go into motion. And that law is also called the law of inertia. And I said inertial is simply the property of a body, okay? And it defines the body's resistance to a change in state. So if a body is already at rest, that body will want to remain at rest. And that property is called inertia. If a body is already in motion, the body will want to continue in motion. That property is also called inertia. So the inertia of a body keeps a body at rest if the body is already at rest. And it also keeps a body in motion if the body is already in motion, right? In either case, if you want to change the state of the body, whether already at rest or in motion, you have to apply a force big enough to overcome the inertia of the body, okay? Now, the second law says that the rate of change of the momentum of a body is equal to the applied force. So when a body is now already in motion, right, the rate at which that motion will keep changing is equal to the amount of force you have applied on the body. That law is the second law of motion, which we sometimes also call the law of momentum, right? The momentum of a body is given as the product of the mass of the body and the velocity of the body. So a body at rest does not have a momentum. A body at rest does not have a momentum because the velocity of the body is zero. So if you multiply any quantity with zero, what you get is zero, right? So a body at rest does not have momentum. So here M is equals to momentum. Okay, now the third law says action and reaction are equal but opposite. If you apply a force, just a quick one. So if you have a body, let's say this is an object, and you apply a force on that body, a force F1, we are saying that this body will react with an opposite force, F2. And what the third law says that F1 will always be equal to F2, but their direction will be opposite. That's what the third law is saying. Okay? Good. We went on then to talk about force. Oh no, I think that was the last. That was where we stopped the last time. Right. So if you have a question, please drop it on the chat box, and somebody will. Rena will help us collect the questions, and then I can answer to all the questions at the end of the class. So very quickly, we are going to go on to forces. A force is that which causes a body or an object to change its state at rest or in motion, right? So before a body can change its state, you will have to apply something called a force, right? So if a body is at rest, you have to apply a force to cause the body to change and go into motion. But if a body is in motion, you also have to apply a force to cause the body to come to rest from motion. Is that okay? Cool. Now, there are different types of forces. I've tried to place two classes. So I have what we call the fundamental forces, and I've also placed another class called the mechanical forces. Now, the fundamental forces are the forces that occur naturally in nature. And there are four fundamental forces in nature. There is the gravitational force. So every body is always on, when I say a body, I mean B-O-D-Y. Every body, or should I say every object? Every object is under the influence of gravity, or is under the influence of the gravitational force of every other object around it. Okay? What I mean by that is, just as you are sitting right now, you are under the influence of the gravitational force of your chair, of your phone, of your computer, of every other object around you. Okay? The extent to which you will feel this gravitational force depends on only one thing, right? So a force of gravity that anybody would experience is a function, or it depends on mass. Sorry, my handwriting is really terrible right now. So this depends on mass. And this mass is the mass of M1 of object 1 and M2 of object 2. So the difference between M1 and M2 will determine how much force anybody or any object will experience. So for example, we can all experience the gravitational force of the Earth. When we throw ourselves up, we will always come down. When you throw an object up, it will always come down. That is the Earth's gravity pulling on the object. And the reason why objects can feel that gravity so much is because most of the objects you see around you, they have a mass that is very small compared to the mass of the Earth. Similarly, the Earth feels the gravitational force of the sun because the mass of the Earth is very small compared to the mass of the sun. Okay? The reason why when you walk on the road, you have dust particles sticking to your clothes is simply because your mass as a human is very large compared to the mass of a dust particle. So the dust particle will easily be attracted onto your body. It's the same principle essentially. So that's why I said every object feels a gravitational force by every other object around it. But the extent to which they will feel that force is simply dependent on their mass compared to the mass of the object around them. Makes sense, right? So next time, if you wonder why just dust particles always stick to your clothes when you are walking on the road, it's simply because you are attracting a gravitational force on those dust particles. Your mass is very large compared to their mass, so you are always pulling them to yourself. Okay? If you try to reduce yourself so small as they are, they will no longer stick to you. Make sense? All right, so let's go on. Then the next one is electromagnetic. I hope I am doing well with time. Okay, the next one is electromagnetic force. Electromagnetic force is a combination of electric force and magnetic force. Combined together, they are called electromagnetic force. They exist in nature. Like I said, electric charge is a fundamental quantity. So it exists naturally in nature. And it generates something called a field around it. And that field around a charge is called an electric charge. So we have something called an electric charge, which is, and then if this electric charge has a field around it, and that field is called an electric field. And that field has an ability to exert a force on every other charge around or within the vicinity of that field. Okay? And if I take you one step back, the reason why every object can exert a gravitational force on another object is simply because every object that has a mass can generate a gravitational field around itself. And that gravitational field can exert a gravitational force on another object that is present within the surrounding of that field. Makes sense, right? So that's how it works really. Similarly, a magnet can generate what we call a magnetic field around itself. And that magnetic field present around a magnet can exert what we call a magnetic force on every other magnet within that field, right? And later on, if we go, further into electromagnetic field, we are going to find that they are both two sides of the same coin. An electric charge can generate a field around itself, and that field can exert what? An electric force on an object. And the interaction of those two can then generate what we call a magnetic field. So when a charge is moving, a charge can both generate an electric field and a magnetic field. It generates an electric field as a result of the charge present inside it. and it can generate a magnetic field as a result of something called magnetic moment of the charge itself, right? So that is why we have classified those two forces to be one, electromagnetic force, because they come from the same thing, which is a charge. All right. The next one is what we call strong forces. Strong forces are forces that are responsible for keeping the particles that are present inside something called a nucleus together. When you study chemistry, remember in the first class, I told you physics builds on the foundation of mathematics, and then chemistry builds on the foundation of physics, and then biology built on the foundation of chemistry. So biology is at the top, at the bottom is physics. At the bottom, sorry, biology at the top, followed by chemistry, followed by physics, followed by mathematics. Mathematics is the foundation of everything. There's no science as pure as mathematics. So the purest form of science is mathematics, because mathematics is what is, in fact, nature and mathematics are same thing. You can't separate it. And every other thing sort of builds on it. This is me preaching, sorry, but that's the basic truth, all right? Biology is just a combination of chemistry, physics, and mathematics. Plain truth. Anyways, I hope there are no physicists and, sorry, I hope there are no chemists and biologists in the class. I remember back in the days, we used to argue a lot. I used to call myself a mathematician. I would say I'm better than everybody because right from very young age, I understood that mathematics was life and every other thing derives their life from it. Anyway. Sorry, my screen has gone off. Right, so the next one is, I said strong forces are simply the forces that are responsible for keeping the particles present inside a nucleus together. And what are the particles present inside a nucleus? So nucleus, sorry. The nucleus of an atom is simply the center of that atom, okay? An atom, we are told, is the smallest particle of a substance. An atom is the smallest particle of a substance. And an atom is composed of something called a nucleus. Inside the nucleus of an atom, we have two types of particles called the protons So an atom has a nucleus, and a nucleus has a proton and also a neutron. So if you assume this to be an atom and you assume this to be the nucleus of an atom, in this nucleus you are going to have protons and you are going to have neutrons. You're going to have neutrons, and outside the atom we are going to have some other smaller particles called electrons. We are told that protons are usually positively charged and neutrons are negatively charged, right? So the thing is that inside the nucleus you have what we call protons, and there's a basic law from physics that says that like particles that are alike always repel each other. So in this very small space of the nucleus, you have a lot of protons that are all positively charged. What they try to do is that they try to pull away from each other because they are alike. So they are pulling away from each other. I know this is very counterintuitive. We are told in life that people that are like always come together, right? You are friends with your friend because you guys are alike. Sorry, but in physics, in electricity, things that are alike always want to stay apart. So because protons are alike, they always want to stay apart. And the only force that helps to keep them together within that very small space is what we call strong forces. Okay? Now, the other type of force we have called the weak forces are what is responsible for the neutron. So a neutron, which is a very tiny particle, sometimes can split. A neutron can split or can sort of, yeah, can split or disintegrate into what we call, so a neutron can split up into an electron and another particle, which physicists call antineutrino particle. So the force that is responsible for splitting a neutron into an electron and another particle called an antineutrino particle is called a weak force. The antineutrino particle has no mass, but this guy has a mass, right? And that the force responsible for that is called the weak forces. Let's not dwell too much on that. Now we have another class of forces that are called, mechanical forces, which are the ones we can feel with, we can easily feel them, we can play with them and things like that. Okay, and they basically come about by motion of a particle. So we have what we call frictional force. A frictional force is that force that tries to oppose a motion. So when you are trying to pull an object along the floor, right, there's a lot of resistance to that motion, and that force causing that resistance is called a frictional force. So if you have an object such as this, object A sitting on the floor, and you are trying to push this object with a force F, there will be another force, okay, acting on this surface where this object is placed, and that counter force is called a frictional force. From Newton's third law, action and reaction are equal and opposite. The force you are applying to pull this object at a given time will be equals to the reaction here, which is the frictional force. At that time, the object will just be at rest, will not be able to move. But if you increase this force that you are applying much enough to overcome the friction, the body will start to move with a velocity v. Okay? There's a third force that will act on this surface, which is due to something called the weight of the object. This object has a weight because of its mass and because of gravity around it. So at the end, we are going to have 4 types of forces acting in this system here. So I'm going to redraw that. We have an object on the surface. This object has a mass m, and so there's a force acting on the center of that object, and that force is actually called the weight of the object, W. And this force or weight always acts downwards. So we have W acting downwards. Now, if you're applying a force on this object to try to move it, let's say you're applying a force F, you are pushing the object. So this is a push. There's a counter force acting opposite due to this surface called the frictional force. And this weight that is acting down, pressing on the surface, there's a counter force that is going to be acting up as well. That counter force is what we call the reaction of the flow on the object. So at the end of the day, we have 4 forces acting on this object. We have the normal force, which is the push that you are applying. We have the frictional force, which is acting on the surface. We have the weight of the object, and we have arrow, which we call the normal reaction from the flow. All these forces are mechanical forces, right? And then we have another force called centripetal force. Centripetal force is the force that tries to keep an object on a circular path and prevents the object from moving out of that circular path. For example, if you have an object, if this is a circular path, and you have an object traveling around that circular path, the object is traveling along that circular path. This object has a mass and a weight. Okay? There will be a force that will keep this object in this circular path. That force will always act towards the center of the circular path. That force is called a centripetal force. And centripetal force is simply given as the product of the mass of that object times the square of the velocity of that object divided by the radius of that circular path. All right? So this force is called a centripetal force. So the reason why, how many of you watch Formula, is it Formula One is called?
Yes. I do.
Yeah. So the reason have you ever wondered why those cars can move very fast around a circular path and then they don't crash sometimes? We know occasionally they crash. But how are they able to spin around a circular path? The simple reason is because the engineers that design a racetrack understand how a centripetal force works. Okay? So the reason the car can stay on that track is because they've designed the tires and the road in such a way that the centripetal force generated on the car is enough to keep the car around that circular path. Now, there's something similar to the centripetal force called the centrifugal force. The centrifugal force does something opposite to the centripetal force. The centrifugal force tries to pull the object outside, away from the circular path. From the Newton's third law, action and reaction are equal. So when the centripetal force is equal to centrifugal force, the object will stay in that circular path. So the reason why the Earth keeps revolving around the sun, and we are not told someday by astronauts that our Earth has left its path and is somewhere in the alternate universe, is simply because the centripetal force and the centrifugal force on the Earth is constant. So the Earth keeps revolving around its orbit around the sun. And that's similar for every other planet, similar for every other star, okay, in their galaxies, as it were. All this can be explained by physics. That's for forces. If you have questions, please note them down. I will run through them. I'm not doing so well with time. But the next thing we're going to look at is energy.
Sorry, you have 12 more minutes.
Yes, I know. So I'm going to try to go through what I have left and then solve a couple of questions quickly. Now, the next thing we're looking at is energy. Energy is simply the ability or the capacity to do work. So when you say somebody has energy, it means that the person has some form, the person has the ability or the capacity to actually do work. And that work can be in the form of running, can be in the form of jumping or walking, or it can be in the form of doing anything really, okay? And that's what we call energy. So energy is just the ability or the capacity to do work. Is that clear? And we have different types of energy. And this type of energy is basically defines where that ability or that capacity comes from. Now we have something called electrical energy. We have something called solar energy. We have something called mechanical energy. We have something called so we can have electrical, we can have solar, we can have mechanical. There's also something called tidal energy. There's something called wind energy. And there are so many other ones, okay? Types of energy. Now, the electrical energy is the one that is associated with an electric charge. So the type of energy that an electric charge has is called an electrical energy, right? And that electrical charge, when it moves, okay, through a medium, it generates something called a current. okay, or it translates into something called a current. So when a charge is moving through a medium, so the medium can simply be a conductor, what we call an electrical conductor, or a wire, or a metal, right? So when the charge is moving through a metal or a conductor, it becomes a current. And that current, when it flows through a given time, it then generates what we call an electrical energy. And that electrical energy can be used to do different things, right? For example, when you plug your kettle into a wall socket and you put water in, first, please put water in the kettle before you plug it. So when you put water in the kettle and then you plug it into a wall socket, after a while, the water becomes hot and it starts boiling. And you are wondering, how is that possible? That is simply possible because there's a charge present in your wall socket, okay, that then moves through the wire, which is the cable of the kettle, into a material inside the kettle, okay, which can be a filament or something, which is another metal, which gets heated up due to the motion of the electrons within that material. That then generates a type of energy called heat energy. That heat energy is what is then translated into temperature that heats up the water, and then you have your water boiling, okay? Now, solar energy is the type of energy you get directly from the sun. Is that okay? Then we have mechanical energy. This mechanical energy is associated with motion, and there are two types of it. We have what we call the potential energy, and then we have what we call the kinetic energy. The potential energy is the energy of a body at rest. So when a body is at rest at a given point, it has what we call a potential energy. But when the body is in motion, is moving, it has something called a kinetic energy. And those are two forms of mechanical energy. Then there's something called a tidal energy, from the word tides, which is the waves from an ocean. Okay, that is the type of energy. The motion of the ocean waves can generate a type of energy called a tidal energy. And actually, tidal energy is actually a type of a mechanical energy because it's a combination of a potential and a kinetic energy. Then we have what we call wind energy, which is the energy from the wind. When the wind is blowing, it has an energy in its motion, right, called the wind energy. It is also actually a kinetic energy, if you look at it critically. Then, like I said, there's the heat energy. Of all these different types of energy, you can store all of them. You can store them up. You can store electric, solar, mechanical, tidal, wind. You can store them. The only type of energy you cannot store is called heat energy. You cannot store heat energy. Heat energy is simply energy in motion. Is what we call energy in motion, or what they call transient. Physicists call it transient energy. So you can't store heat. So heat will always move from one body to another. It cannot be contained within one body, right? And it moves whenever there's a difference in what we are going to come to that. When there's a difference in temperature between two bodies, heat will simply move between those two bodies, right? Work. What is work? Work is simply the product of force applied on a body, okay, and the distance moved by the body. So if I have a body sitting at a point and I apply a force to this body F, which causes this body to move along the surface to another point. So let's say this is the position the body was, position A, and the body has now moved to position B due to the application of this force, covering a distance D. So the distance between this point and this point is D. The work you have done in moving the body from A to B, the work done is simply the product of force and the distance the body has traveled. Okay? And if they now ask you to calculate the energy that you have used in doing this work, the energy you have used in doing this work will simply be the product of the work that you have done over the time it took you to do that work. So your energy, E, will now be force times distance over time. All right? Now, what is power? Power is the work done over a given time. Okay? So power will simply be energy times, oh, we're going back to where we are coming from again. Yeah, essentially, energy times time. Okay, such that if you were to go back to this equation, this is becoming a bit mathematical now. It almost seems as if power and work done are the same thing, which in reality are the same thing, really. Okay. So I'm just quickly going to solve some practical questions. I was hoping we'll be able to talk about temperature and heat, but I have already mentioned about temperature. Temperature and heat. I told you heat is a type of what? Energy. Why temperature? Temperature is a fundamental quantity, and it gives you the measure, or what we call the degree of hotness or coldness of a body. So temperature is a property of a body, but heat, temperature is a property of a body, but heat is not a property of a body. So you can say that this body has a temperature of 20 degrees Celsius, but you cannot say that this body has a heat. I cannot just say I have a heat of 20 joules, all right? So the unit of energy is called joules. So I can't say I have 20 joules of heat, but I can say I have 20-degree temperature. So temperature is a property of a body, but heat is a form of energy in what? In motion. And there are different units for measuring temperature. There are what we call the degrees Celsius. There's what we call the Kelvin. There's what we call the Fahrenheit. There's another one called Rankine, which is hardly used. Okay, this is usually used for engine design, people that manufacture car engines or jet engines, because it's a higher unit of temperature. But we have what we call degrees Celsius, Kelvin, and Fahrenheit. Okay. Heat is energy, so which is what? In joules. Yeah. So let's just quickly take some practical questions to solve and see how we actually apply some of these things that we have learned in solving practical questions in school. Here you have a question. This is a GCSE question. We are given a figure and we are told that the force is acting on a child who is balancing on a pogo stick. The child and the pogo stick are moving. How many of you can relate with this figure? Can everybody relate with this figure? Hello? Yes, okay, somebody say yes. Right, so this is something you can stand on and you can jump about and can move you around, okay? Now we are told that the downward force on the child on the spring is equal to the upward force of the spring on the child. This is an example of which law of Newton's laws of motion. So basically we are told, what we are told from that question is that we have a boy standing on a spring, and the downward force of the boy, which is the weight of the boy, hopefully, is equal to the upward force of the spring on the boy. Now, if F is equals to F sub X or Fs, what law is this? Can somebody unmute himself? Right, somebody said third law, so that's correct. So the answer is what? Third law. Okay, Now, if we go on, they said complete the sentence. Use an example from the box. Elastic potential, gravitational potential, kinetic. The compressed spring stores what type of energy? The compressed spring stores what type of energy? Now, if we go back, somebody said elastic, right? That is actually correct. It's actually an elastic potential energy. I know I didn't talk about that type of energy. So when you have a spring, okay, there is an energy stored in the spring due to a property of the spring called the elasticity of the spring, okay? And that energy is actually a potential energy because the spring is at rest. When you stretch it, that potential energy becomes released, okay? And you can use it to do a lot of things. For example, you can clearly see how it is used in motion by the boy, okay? Gravitational potential, that is wrong. We've talked about that. That has to do with the mass of a body. Kinetic, that's okay, energy in motion. But because we are, the question specifically said compressed spring. So the energy stored in compressed spring is potential, elastic potential. Now we are told that the child has a weight of 343 newtons, and the gravitational field strength around the child is 9.8 Newton per kilogram. Now we are asked to write down the equation that links the gravitational field strength, the mass, and the weight of the body. Right. If we go back to this, the force acting on every object due to the weight of that object is called the Earth's gravitational force on that object. And it is simply given by the product of the mass of the body, times, remember, I've told you that force is a product of mass times acceleration. In this case, the type of acceleration we are looking at is a different one, and it's called gravitational acceleration. And we normally represent it by the letter G. So this force we are looking at here will be a gravitational force, which is the product of the mass of the body and the acceleration due to gravity. So acceleration due to gravity. And so the force will be given as the mass of the body times the acceleration due to gravity, G. If the body is a free body, then this force will be exactly equal to the weight of the body. So the weight of the body is given by the product of the mass times the acceleration due to gravity. So when you throw an object up and the body is free, or the object is free in air, the weight of that object is equal to the Earth gravitational pull on the object. And it is given by the product of the mass. It's given by the product of the mass, and the acceleration due to gravity, which is the acceleration the body will use to travel to the ground. Okay, so if we go back to that question, sorry, I'm just jumping about on my screen. If we go back to that question, they said we should write the equation that links the gravitational field strength, the mass, and the weight. Now, the gravitational field strength is equal to the force anyway, the force on the body. Right, so I am not doing very well with time, but that was just an example to explain certain things to us. So another question here, which has to do with a moving car on the surface. And we are asked, which one of the statements describes the motion of the car? Tick the box. It will be moving down, it will be stationary, it will have a constant speed, it will be speeding up. Now, if you look at this diagram, we are told that there's a force pulling the body in that direction. 800 newtons is pulling it to the right, and there's another force, 800 newtons, pulling it to the left. What will happen to this body?
It will be at a constant speed.
It will be at a constant speed. That's correct. Does anybody have a contrary answer?
It will be moving at a constant speed, but it won't have any acceleration because there's no unbalanced force.
That's very correct. Remember, Newton's law, first law says that a body will remain at rest or in motion except you apply a force to counter that state. Although there are forces acting on this body in motion, it will not come to rest, neither will its motion change, because the forces acting on it, they are equal, but they are opposite, which is what the third law says. Right? So this force will cancel out this force, and so whatever the body is doing, the body will keep doing it, move at that constant speed. So it will have a constant speed. That's correct. I'm just going to stop there for now, for the sake of time. So any questions?
Thank you very much, Emmanuel. We'll move over to Orena, who will take the questions. So if you have any questions, can you please put it down in the chat?
Thank you, Emmanuel, for that wonderful presentation. I have a few questions here from David B. and one from Ibuka. So David B had asked a question here. He was talking about finding resultant force. So how would you find resultant force? That's the first question from David. Would you want me to ask all his questions, or do you want to?
Yes, ask all his questions and I can take everything. Yeah, please.
So the second question he has here is, he says here, is it based on friction? So I think he was asking a question based on the motion of an object.
Right. So how you find, yes. Okay, go ahead. Sorry.
The third question he's asked is, how does a train wheel move? Or how does a train wheel work? So I guess something that has to do with force as well.
Yeah. All right. So the first one, how do you find a resultant force?
Sorry. There's a last question, Orena, in the chat. I don't know if you want to add that one.
That's from Ebuka Okoye. So I was thinking he would finish up with David.
Okay.
Right. So how you find the resultant force acting on a body? So if you have a body, all right, okay. You have this interesting guy, okay? You have this interesting guy, and there's a force acting on this guy, pushing this guy. There's a force A pushing this guy. Are you there? And there's a force B pushing this guy. Again, this guy has a mass, so he has a weight acting down. Okay? And hopefully the guy is standing on the ground. And so there's also another reaction from the ground, R, which is a type of a force. What will happen to this guy if we have all these four forces acting on the guy? What will simply happen to the guy is that if you look at the horizontal force, so the horizontal force or the horizontal forces are FA and FB, the forces acting horizontal. That is what we mean by horizontal. So if you look horizontal, the forces are FA, FB. So if this is acting to the right and this is acting to the left, this is acting downwards and this is acting upwards. If you sum up the forces acting horizontal or to the left and to the right and assume that the right is positive and the left is negative, the sum of the forces horizontal will be FA minus FB. Okay? While the forces acting vertical, this is what we call vertical, okay, up, down, which is upwards, downwards. Vertical forces, the vertical forces are simply the weight, W, and the normal reaction from the ground, R. And so the vertical forces will be equal to W minus R. So let's add numbers to these figures. Let's say a force A is 5 Newton. And let's say the force B, sorry, I'm going to pick up another pen. Let's say the force A is 5 Newton. And let's say the force B is 3 Newton. Let's say the weight of the object is actually 10. Let's say the weight of the object is 10 Newtons. And the normal reaction is 10 Newtons. And you're asked to find the resultant force. So a resultant force is simply the sum of all the forces acting on an object. That will simply be, if you look at the horizontal, it will be 5 minus 3. That is 2 Newtons. And if you look at the vertical, it will be 10 minus 10, which is what? 0. So the resultant force acting on that object will simply be 2 Newtons. So this boy is going to be walking because the final force is a pushing force. I intentionally put 10 and 10 here to actually make a point. If this force R and W are not equal, the boy will either go up or go down. So let's assume that the weight of the object, of the boy, is more than the normal reaction. What will happen is that the boy will collapse into the ground. That's plain physics. Okay? Similarly, if the normal reaction from the ground is more than the weight of the boy will be floating. Okay? But what happens is that the reason why you can walk on your ground is simply because based on your weight, every time you stand on the ground, your weight will always be equal to the reaction from the ground. So you will be on the ground. If anything happens and your weight is less than the reaction from the ground, you will be floating. So for astronauts who go into space, the gravitational force on them is the G is smaller than what you have on the ground surface. So the G in space is less than what you have on the Earth's surface. On the Earth's surface, G is 9.8 meters per second squared. But in space, G is far less than this value. So it means that the weight of the object, which is its mass times gravity, will be less than what it would be in space than what it is in Earth. So when the body will not be able to stand on a solid surface, it will always be floating because the normal reaction will always be more. Okay, that's what we call gravitational levitation. We call it levitation, which means a body will naturally float in space because G is lesser than the value on Earth. All right. There was another question I forgot to answer.
So the second question which you hadn't answered was how does a train wheel move? Is it based on friction or?
How does a train wheel move? A train wheel moves on, there are so many things that contribute to the movement of a train wheel, right? Again, it depends on what type of train. If it's an electric train, first, the motion starts with the overhead lines. You see those electric lines that you have overhead? The train connects to it, and the voltage on that lines are connected to the motor inside the train, which powers the motor. And that motor causes some kind of motion on the wheel, right? Yeah. And then combination of the wheel, the friction between the wheel and the rail, which is the rail on the ground, causes the motion to be constant or keep moving. Okay, so it's a combination of the frictional force between the wheels and the ground. Okay, otherwise the train will suspend off the ground. There's another type of train that actually does that. It's called maglevs or magnetic levitation trains. There's another principle for why that is possible, right? So basically, it's a combination of the friction of the wheels and also the motor which drives the train. That's if it's an electric train. Then if it's a normal diesel train, the whole type of train that we call locomotives, the principle is still the same. There's an engine within the train called a combustion engine, which can either be burning diesel if it's a diesel train or a fuel train, or if it's the hot coal train that uses coal. So you are burning the coal is generating a lot of heat. The heat is then used to heat up water to generate something called steam. The steam, when it travels at a given speed, can apply a force on the wheel which moves the train. So yeah, those are the three types of train, and that's how they all work.
All right.
Thank you. Thank you.
Thank you, Emmanuel. So we've gone over by about 8 minutes. Ebuka has asked a question here. I think he was trying to clarify if there was an equation for energy divided by power. And then Noke has asked a question about atoms, if atoms have any color. And she's also asked if normal reaction is known as upthrust.
If normal reaction is known as upthrust, yes, normal reaction is same as upthrust. For example, if you put an object inside a fluid is either water or gas, right? So if you put it inside a fluidic medium, like they are called, let's just, for simplicity, let's say water. If you put an object inside water, for example, a boat standing in water, the boat has a weight, okay? And that weight will press on the water body, and that water body will exert an equal force on the weight of the boat. That upward force is called an upthrust. Okay, when the upthrust is equal to the weight of the boat will float, will just float. If the upthrust is not equal to the weight, the boat will sink. Is that clear? So yeah, that's correct actually. And there's a principle for why an object can float in water. That principle is given by an interesting man called Archimedes, okay? And the principle is called Archimedes' principle. Archimedes' principle simply says that when an object is placed in a fluid or water, it's going to displace an amount of the water equal to its weight. So the volume of the water the body will displace is equal to the weight of the body, okay? And that is the reason why an object can float. We are told there's an interesting story where the man was sitting inside a bath, and all of a sudden he realized that he can actually float inside the bath. And he got off the bath and he ran outside and started shouting, "Eureka, Eureka, Eureka," meaning, "I have found it, I have found it." We were told that the guy ran out naked. That's an interesting story, but it's a good way to actually remember the principle.
Thank you so very much, Emmanuel. That was amazing. From the types of forces, even I learned some things. Did you have a good time? Did you all learn one or two things?
Yes, sir.
Yeah.
Yeah.
Awesome.
Yes.
Thank you so much.
Yeah.
Just to let you know, there'll be another last session next week called the bits and bytes of computing. And that would take an hour and a half. Emmanuel will be talking about the A to Z's of computing, everything about how a computer works. And in the last 30 minutes of the session, we're going to do a competition. So get your competition hats on. And after that, there'll be a winner, and the winner would get a prize. So tell your friends, tell people in your school, your friends at school, your friends everywhere that there'll be a competition after the next session. So go onto the website, afb.org.uk, and register for the next event, okay? If you have any questions as well, you can just drop it in the chat below just before the meeting is over, and we'll take it at the next session. Thank you guys for coming. Take care and have a good week ahead.
Thank you.
Thank you, Emmanuel.